Okay, thank you, Marcy, and thank you everyone for joining us. As Marcy mentioned, I'll be starting off this presentation and we'll be presenting on the 2015 NDS changes from the 2012 NDS, and then Buddy will be following up midway through the presentation to bring some variety to this webinar for you. This presentation is copyrighted by the American Wood Council, and if you'd like to use any portion of the presentation, please contact us and we'll help expedite that process. For those of you that are asking, yes, there is a copy of the presentation available that can be downloaded from our website, and I believe Brian is providing that link in the chat box to you. It is available, and for those of you, it's a PDF version, and within that version you'll see a copy of the course description so that when you use it later in a resource you'll be reminded of what this presentation is about. Now, the learning objectives today are to be able to understand the load and material resistance design process and how it applies to structural design, wood structural design. We'll become familiar with the changes between the 2012 and the 2015 NDS. And then we'll look at also identifying the similarities and differences with respect to ASD, allowable stress design values, and behavioral equations. And then also, for those of you that aren't familiar with the overall format and content of the NDS, you'll become familiar with that, hopefully. We'll go through chapter by chapter. And then if you are used it before, maybe this will be a review for you, and it'll help you design a little easier with the NDS, becoming more familiar with where everything is. Now, our first poll, and again, these polls are not the correct or incorrect answers is not dependent on you getting a certificate. So, Marcy?
All right. Let's go ahead. What is your profession? Architect, engineer, code official, building designer, or other? All right. I will hold the poll open until about 80 or 85% of you have voted, and then I will close. Or about 30 seconds, whichever comes first. All right, and then let's share that. Wow, the majority of you are engineers, 85%.
Wow.
And a little bit of everything else. No building, well, one building designer it looks like. All right. Oh, and I guess, Michelle, you can't see it. So 85% engineers, 88% code officials, 4% architects, 1% building design, and 2% others. So.
Great. And we've got a lot of people, a lot of engineers, it sounds like. So the correct answer is, no, I'm kidding. Well, thanks. We welcome you, and it's great to see all of you, or hear all of you. Well, we're not hearing all of you. Anyway, to see that there are a lot of people on the webinar interested in learning more about designing with wood.
Michelle, this is Buddy. We're not seeing your screen.
Okay. Did you see it now? We had this technical difficulty before.
Nope, we're not seeing it. So
we didn't change presenters, so I'm not sure. Let me click on it, and this is, sorry, audience, we've had this issue before. Now?
There we go.
Good. Okay, you're up.
Okay,
you're up.
Thanks. Okay, so you're seeing the poll question. Okay.
Yep.
Hopefully, well, keep giving me a tip if you don't see me.
Okay.
Okay, so now we're on to the next. Let me click on this. I don't know what's going on with GoToWebinar this morning, but we'll go through it. So to give you a preview of what we're going to be doing throughout the presentation, we're going to look at an overview of AWC and the developments of the standards. We'll look at the design process overview, the assumptions that are made when developing the standard, and then we'll go and look at the actual publication, the NDS publication, and do a chapter-by-chapter discussion, and also highlight the significant changes from the 2012 NDS to the 2015 NDS. And then also, Buddy will sum it up at the end on a summary of the changes and also where you can get more information. Okay, historically, this shows you the publications that were developed throughout the years for designing with wood, starting off in 1944. The first publication for national design specifications for designing with wood was developed by USDA and Forest Products Lab. And as you can see, similar with other standards, we've incorporated more and more information related to wood. And eventually it was then taken over by the AFMPA, which many of you probably are more familiar with than AWC. AFMPA is the American Forest and Paper Association. And then up until, well, it's been the most current one now. Well, under the 2012 IBC, the 2012 NDS was adopted, and then the 2015 NDS is the one that we're talking about today. And if you're interested, AWC does have archival versions of these, so you can contact us if you're dealing with existing buildings and you're interested in finding out how they were, what standards they were used back when they were designed. We do have those available. And as I mentioned, the 2015 NDS is referenced in the 2015 IBC. And that gives you similar graphic design. I'm showing a real long delay between the two. There we go. And for those of you that don't know, for the first time in AWC history, I don't know if it's in AFPA history, but the NDS is available for a free download from our website. And it is a read-only version, meaning you can't make copies of it. It does not include the commentary. That may come later, but right now the electronic version does not include the commentary. So if you go to www.awc.org, you can download the NDS. And that is true for our other 2015 standards that are available, meaning the wind and seismic provisions, the wood frame construction manual, etc. Those are all available for a free download. The other thing I want to point out is that the AWC is the ANSI accredited standards developer, and we became that in on March 29th, 2011. Previous to that, as I mentioned, it was the standards developer was AFMPA. And you'll notice that in IBC, when we reference the documents, you'll notice a change from AFMPA to AWC in IBC and IRC. And the other thing I want to point out is this standard is developed through a standard consensus-based process, and our consensus body is the Wood Design Standards Committee. So this is a very rigorous process where it's not only the wood industry that's involved with developing the standards, but we have a cross-section of stakeholders that are involved that are also involved with the process of developing the standard. Boy, that was a tongue tire. Okay, so I know you are on the edge of your seat and you'd like to know what are the major changes that have been incorporated in the 2015 NDS. This gives you an overview of it. We have new provisions to address CLT, that's cross-laminated timber if you're not familiar with CLT, charging language related to CLT, design values, design equations, product chapter, connection design, and fire design. And we'll get into these later in the presentation. But that gives you a broad overview of the primary changes in the NDS. Okay, now looking at the overall format of the actual NDS and the changes from the 2012 to the 2015. The 2012 NDS is formatted such that the chapters 1 through 3 cover general design criteria or general provisions for designing with wood, and then the product chapters, meaning when you get into sawn lumber, I-joists, glue lams, structural composite lumber, oriented wood structural panels, those are all in the product sections, which are in chapters 4 through 9. And then connections are in 10 through 13 in the 2012, and then 14 is shear walls and diaphragms, and then specific loading is in 15, and then fire design for fire is in chapter 16. Now when we go over to the 2015 NDS, chapters 1 through 3, same format that still covers general. Now what changed is in chapters 4 through 9, because those dealt with the products and we wanted to keep the wood products together, we've added a chapter 10, which is the cross-laminated timber. And because of that, the subsequent chapters 10 through 13 now become 11 through 14. So 11 through 14 is connections, and you're wondering, okay, so what happened to the shear wall and diaphragms chapter? Well, chapter 14 in the 2012 NDS actually just had a one paragraph or one sentence that's referred the designer to the wind and seismic provisions. So now we eliminated a chapter specifically for that and moved that paragraph into the general chapters, and I'll point that out specifically when I get to that section. Okay, and then because we eliminated that section for shear walls and diaphragms in chapter 14, chapter 15 and chapter 16 remain the same. Now the design process. How do we design our buildings, and what criteria or what method do we use to design? For those of you that have been in the industry are probably quite familiar with this process, but for those of you that are new to the process, perhaps this will be very helpful to understand the design process as it relates to ASD and LRFD design. Now when we design a building, we have obviously a demand, what are the loads that are applied to that structure, and then there's a capacity, the structural resistance to that. How is the structure resisting those loads that are being applied? And so the design process, when we look at the demand, we have load, support conditions, geometry, and those demands could be based on type of loads, the magnitude and placement of the loads in the system, and resulting interaction of those loads. And then the capacity, and it also includes the capacity side, which includes also geometry, materials, and performance. So it would be the material choice, the section geometry of what you're utilizing to resist those loads, and how the system behaves under those loads. That would be the capacity side. And beyond that, also, you may want to also look at fire, resistance to fire, something that's becoming more and more prevalent in the U.S., where the engineers are getting more and more involved with the fire resistance. And then the economics of is it buildable or is it constructible? Some engineers may get involved with that, or designers pretty much, or the aesthetics. So that's the other aspects of the design process. Now when we look at that, when we evaluate a structure, we look at it from two basic limit state concerns. How we evaluate whether or not this structure will meet our criteria. The two limit states are serviceability, performance, where it's going to be performed, how it's going to perform in service, and then also safety against collapse or failure. And we'll look at that in more detail in the next couple of slides. Okay, serviceability. Both ASD and LRFD design look at serviceability, and they use unfactored loads. Both processes use unfactored loads, and we also use mean material strength values. And one way of looking at it is serviceability. So you have a floor and you're evaluating a floor, the serviceability of the floor. There are certain criteria under unfactored loads. You want to know, and you have a criteria, a certain deflection, L over 240 for that floor or L over 360 for that floor. And beyond that, that's per code. Beyond that, you may want to also look at what your feel for that building should be, whether or not you're going to get a bouncy floor, what the criteria from the owner is going to be, and whether it's not going to be a high-end residential where you're going to want a very not a bouncy floor. So there's even other parameters beyond that. Now, for this, what we want to do is, in serviceability design, it is possible to determine structural performance with a good level of precision. And for this reason, it's important to know how well the structure is actually performing. And a way of seeing this is to consider the average material strength values in combination with real, that's why we deal with the real loads rather than factored loads, to see the actual performance. Now, the second limit state is where we deal with the actual safety of the building, whether it's going to collapse under certain loads. With safety, on the other hand, we're dealing with, we can think of it as statistical terms, probability of failure, or conversely, survival, conversely. So what's the probability of it's going to survive? And using statistics, one can appraise the safety of the structure in terms of measurable probability. So for LRFD, we deal with factored loads, material reference strengths, and resistance that are tied to statistical data, which I'll get into in the next slides. However, with allowable stress design, we're dealing with unfactored loads, and we're dealing with material strength values. And because we're dealing with unfactored loads, we have a high factor of safety on our material strength. So again, ASD, we're dealing with unfactored loads, high factor of safety on our material strength, and LRFD, we're dealing with load factors, material reference strength, and resistant factors that are tied to statistics. So how does this all play in with statistics? This is a representation, or a symbolic representation, of structural property variabilities. On the horizontal axis, we have material properties values. You can see that they have, we have, let me get my mouse, structural composite lumber, I-joist, glue lambs, MSR lumber, and visually graded lumber. And on the vertical axis, we have the relative frequency. So for example, and these are normalized distribution, normal distribution curves. So the area under the curve is equal to 1. But what we see is, for the members that are tested, we record a relative frequency on when they meet that certain property value. And then from that property value, it may vary. So X is the mean here. And then from that mean, how often does that member resist it away from that mean? So the relative frequency. As you can see from structural composite lumber, it's a very highly engineered wood product. So we don't stray very much from that mean value. However, for visually graded lumber, where it's not a highly engineered product, it's a natural product, you're going to have some variability in the product. You can see it has a flatter curve from that mean. Now, also on this curve, you'll note, is there's load in pink. So we have an applied load and we have a resistance, the resistance. And from this, we can also come up with a presentation of a resistance and relative, well, we can take two curves from that. Let me back up a little bit. On the left side, we have the load. So let me go back to that slide. We have the load, and then we have the resistance. We can take a representation of that, and again, we have the load here and the resistance here. And what this shows is where this overlaps, that is where the actual load is greater than the resistance, and that's where we have failure. Now, taking that even one step further, so this just shows you in this area where they overlap, we have failure. Now, taking this one step further and normalizing the distribution curves, we have a safety function Z that we can determine. And over here we have the mean value of that, taking the two curves, so we subtract the load from the resistance, and then we have a normalized curve, and you can see 0 is no failure, to the left, to the right is no failure, and to the left is failure, because that's where they overlapped. So this now provides us with a method of measuring that actual failure, or the probability of the failure actually. And it's represented by this beta, this safety index or reliability index here. So how does this all apply to the what we do as designers? Let me go here. So that's the probability of structure. We use this data, and we use the from the measurements that we had. Let me go back to this. From all of these resistance measurements, we use the 5th percentile of tested data and come up with our resistance for our structural wood members. Let me go back further. So when we compare allowable stress design to LRFD design, right here we're showing on the left side we have an estimated load, whatever load we're applying to the structure, and then we use that for our design. Our loads that are applied are not factored up, and because of that, on the resistance side we have a high factor of safety. So the materials, the strength of the materials are adjusted to that with a high factor of safety on the resistance side, and hopefully your design load is less than your adjusted resistance side. Now on the LRFD design, we have similar equations where we have the demand on the left side, the resistance on the right side. Now on the demand side, we have estimated loads similar to allowable stress design, but we factored those loads based on research that was done, and in our case, in the 80s, we did some research with ASCE to come up with our design values, but our factors, and now we have factored loads. So we have factored loads because of all that research that was done, and they're higher than the estimated loads or the applied loads. And on the resistance side, we now have a factored resistance, but because we know more about what's going on with the load side, our difference between the tested membered resistance and the factored design is less. So we have higher resistance. Okay, now going into how does that apply to our designs? Well, under the 2015 NDS, similar to the 2012 NDS, we have adopted ASCE or reference ASCE 710. So nothing changes there from the 2012. For LRFD, we have the basic load combinations, and this is very similar to all other materials related to that are designing using LRFD. And then on the ASD side, we also reference ASCE 710 for our load combinations, and you can see they're similar to what we've been using in the past years, although the snow loads have changed a little bit because now the snow loads are based on, or the snow maps are based on a strength design, and that the load combinations for both LRFD and ASD have been adjusted for that. Now, if you're interested in finding out more information for LRFD versus ASD and some efficiencies that you can find out in LRFD, we do have a white paper that's freely downloaded from our website. I should warn you, though, that this is based on ASCE 702. Hopefully it will be updated in the future, but it'll give you an overall idea on, and it's also based on 2005 NDS, but it'll give you an overall idea on the load combinations that lead to efficiencies when you're looking at LRFD versus ASD. So one thing I want to more point out is when you go to the document and you're designing for ASD or LRFD, there's some things you need to know. We go to the NDS supplement to get our reference design values. These give our resistance side of the equation, our capacities of our wood members. And when we go there, that document, the NDS supplement, was based on an ASD design. So rather than having two documents, one for ASD and one for LRFD, we now have this conversion factor, which is KF. So on the top, we go to our NDS for allowable stress design on the top right here. And we go to the NDS supplement to get our reference design values, and then we multiply it times a load duration factor. If we're doing LRFD design, we again go to the NDS to get our reference design values, and we multiply it times a K factor, which is a conversion factor, format conversion factor, to get it into an LRFD design. And similar to ASD, where we have the load duration factor that's based on the how the length of the loads that are going to be applied to the actual structure or member, we have a time effect factor, which is lambda. Let me see, I'm missing right here. And then we have a phi factor, which is the resistance factor, which I'll mention further in the slides, related to LRFD. And that has to do with the types of loads it's being resistant and the ability of the material to resist that loads. Oh, here it is. So this is the resistance factor, the phi factor. It's for LRFD design. And I'll discuss this later on in the presentation, but we have a table in Chapter 2 that gives you the actual resistance factor. And we have a time effect factor, which I'll mention later on in the presentation and get into it more in depth for LRFD design. And then we have that format conversion factor, but I'll get more into it also later in the presentation. Now, Marcy, we have a poll.
All right. Can everybody hear me? All right. The factor K sub F converts ASD material values from the 2015 NDS supplement for use with LRFD. True or false? All right. Wow. The answers are rolling in. All right, we've got about 35 seconds. I'm going to go ahead and close the poll and share the poll. 87% true, 13% false. And the real answer is, Michelle?
Okay, I'm waiting for my screen to show.
Oh, we see.
Cool. All right.
So that's good.
87% got it right. That's excellent. Yes, the factor K is a conversion factor which converts ASD material values from the supplement to for LRFD design. True. Excellent. Thank you for participating in our poll. Okay, now we're going to dive into the body of the NDS. We'll go chapter by chapter discussion regarding and look at changes from previous editions and then summarize it. As I mentioned in the beginning, chapters 1 through 3, those are general information related to designing with wood. Then we deal with the actual framing member, the wood framing members, going from 4 through 10, which deals with the sawn lumber all the way up to the cross-laminated timber. And also changing to chapter 11 and 14 dealing with connections. And similar to 2012 NDS, we have chapter 15 being special load combinations, and chapter 16 is fire design method for wood members. And then our supplement, this gives you an idea. The chapters that are covered: sawn lumber grading agencies, species combinations, section properties, and then the meat of it, the reference design values, covering sawn lumber and timber, MSR and MEL lumber, and decking, non-North American sawn lumber, structural glue laminated timbers, and timber poles and piles. And you'll probably notice that not all wood framing members are listed here, and that has to do with the framing members being proprietary members like I-joists are not listed in the supplement. And then the appendices, we have in the appendices all sorts of other or additional information to assist you in your design. One thing I want to point out is that of these chapters, A through N, only N is a mandatory appendice, and that has to do with the LRFD design. But there's a lot of additional helpful information here that to help you and assist you with your design and provide more information. The other thing I want to point out is in the actual NDS publication is the commentary, which will be available. Maybe Buddy will mention it later, but it will be available. Currently, it's not available right now for the 2015 NDS, but certainly the previous publication, 2012, 2005, there's a commentary where you can get more information. Okay, now on to Chapter 1, and this deals with general requirements for structural design, so applying to all structural wood members. Chapter 1 deals with the terminologies, definitions, and as you can see, this is an example of bending where we have the applied bending versus the resistance or the demand versus the capacity. Remember, we go to the supplement to get our reference design values, and once we provide all the applicable coefficients or applicable factors, it is the adjusted design values that we check the demand against the capacity. So this is the capacity side of the equation. And so moving forward throughout this presentation, or the NDS, we're going to be dealing with the resistance, the capacity side of the equation. As I mentioned previously, Chapter 1, we do adopt or reference the ASC 710 in both 2012 and 2015 NDS, so no change there. Nothing, and then the reference loads, minimum load standards are referenced. Now here's the charging language for utilizing wood using the NDS. You can see that cross-laminated timber is now specified in the NDS, and this is very important. So under the 2015, now you won't have to use an alternate means and methods for designing cross-laminated timber. Now it's referenced in the NDS. And then I mentioned previously about moving Chapter 14, where it references the special design provisions for wind and seismic. We've moved it from Chapter 14, and it's now referenced in Chapter 1, if you go looking for it. On to Chapter 2. Chapter 2 deals with design values for structural members, and this is where we get into the applicable factors related to all wood structural members. Here deals with the only for LRFD design, where we're dealing with the resistance factor that was mentioned previously, and then the conversion factor, which is dealing with converting the supplement values, the reference design values in the supplement to an LRFD design. And then within Chapter 2, we direct the designer to go to Appendix N to get the adjustments for time effect, similar to LRFD. The difference is that for the LRFD design, it's based on a 10-minute baseline, whereas ASD is based on a 10-year baseline. So you can see there's a bit of a difference in the actual factor. For short-term loading, we're at 1.0. That's that 10-minute baseline. And then when we get into long-term loading, it's 0.8. And then for permanent loadings, we're at 0.6. In Chapter 2, now, for ASD, we have a baseline of 10 years. Just real quickly, so C sub D, which is the load duration factor for permanent dead loads, we have a 0.90. 10 years, we have for occupancy live load of 1.0. And then 2 months for snow load is 1.15. Then we have 7 days for construction loads is 1.25. Short-term loading, which is wind and earthquake loads, and previously it's 1.0 for LRFD, whereas for ASD design it's 1.6. And then we have an impact load duration coefficient of 2.0 for impact load. Now also, with all wood structures, or any structure even, we want to understand what is the end use or in-service use of that building. And with that, we can understand what applicable loads are applied to the wood members when we're doing our design. One of those adjustment factors has to do with temperature. wood, when it's exposed for a sustained period of time for high temperatures up above 100 degrees, a temperature factor will need to be applied to that design. And then, so we often get the question, okay, well, what happens if you're in an attic where you get a diurnal effect where you get heating during the day and then cooling off at the night? Well, then the temperature factor would not apply unless it's at night it's over 100 degrees, but typically you don't have, it's not a sustained period of time where it's going to be exposed to that over 100 degree temperature. It's where you get into the cooling tower conditions where you may have to use this factor or apply this factor. Also, we get questions related to wet service factor and when does that apply. And again, this has to do with where you're going to be exposed to moisture for a prolonged period of time for this moisture. And here's a indication of what we're talking about when we're talking about moisture. This graph shows how wood in the right conditions of environmental temperatures and relative humidity can reach equilibrium moisture contents of 19% or more. And on this horizontal axis, we have relative humidity from 0% to 100%. And then on the vertical axis, we have 0% to 30%. We have the wood equilibrium moisture content. So as you can see, the different graph shows, or different lines show 130 being yellow, 70 degree temperature being pink, and then the dark blue being 30 degrees. So with all those various temperatures, even at low degree temperatures, given the high relative humidity, you can get above 19% moisture content, which would be right about here is where we would be for above 19% moisture content. So understanding the end use or the in-service use of your structure is very important. And this moisture issue also may change the structural properties of the actual wood members, but also you have to think of durability considerations related to moisture. This graph shows you what can happen with certain percentages of moisture content. Of here, we're starting out at 12% moisture content in the wood member, and then on the vertical axis is the strength of the material. So we're at 100% strength, and as the moisture content of the wood increases, you can see a change in the actual strength of the wood member. For impact strength, we actually see an increase in the strength with moisture content, but then the other property values, modulus of elasticity, modulus of rupture, we also see a decrease in the strength, and especially for crushing strength, great decrease in the strength as the moisture content increases. Now, this is the actual factor that's applied, wet service factor that's applied, and you can see, as I mentioned previously, when we're dealing with compression perpendicular to grain, we take a huge reduction of 33% because of it being above 19% moisture content for its exposure when it's in service. Also in Chapter 2, the inclusion of cross-laminated timber in the language for the adjustment factors and for the reference design values. Certainly it references cross-laminated timber. Since cross-laminated timber is a proprietary member, you'll need to see the manufacturer to actually get the actual reference design values, but all the applicable factors will apply to those reference design values that we mentioned here. Okay, now on to Chapter 3, where we get into the behavioral equations. This is the design provisions and equations which we evaluate the wood members by. Similar to other materials, we have shear, bending, deflection, and this is an example of the ASD versus LRFD. We mentioned this previously about the adjustment factors. So ASD is just that. You get your reference design value, bending for example, and then you add you multiply times the load duration factor, and then all the adjustment factors that apply. And then LRFD, we have the reference design values multiplied times the conversion, and then the resistance, and then also the time effect factor, and then all the adjustment factors. Behavioral equations, just some things I want to point out that have changed within the past 2 versions, having to do with the stability, beam stability factor, C sub L, when we changed over to a combined LRFD to ASD format. We have to introduce this E minimum into the critical buckling design factor, and the E minimum takes into account the 5th percentile modulus of elasticity value, so that's something relatively new to the other versions. And similarly for column stability, C sub B value, we also have the E minimum introduced related to that. To obtain the E minimum, or the modulus of elasticity minimum, we have those located in the NDS supplement. You can get those for right there in the supplement, or if you really want to sharpen your pencil and get the exact E minimum, we have an equation that's available for sawn lumber and glulam beams. The reference modulus of elasticity for beams and column stability, E minimum, is represented here. And again, it's which represents an approximate 5% lower exclusion value on pure modulus elasticity, and then you divide it by 1.66 factor. The factor of safety can be calculated using that equation. Okay, the behavioral equations, we have tension, similar format, ASD versus LRFD. So there's tension. One thing to be aware of with tension perpendicular to grain, it is not recommended to apply loads in this situation. There are some minimum recommendations that are in the NDS related to applying loads in this situation, but it's not recommended. Some of the initiators of this tension perpendicular grain is notches, moment connections, or hanging loads. If you look at the commentary, that provides some additional information in the 2012, not yet in the 2015. But this is the Achilles heels of wood members, is this tension perpendicular to grain. So we want to try and avoid it as all possible. We also have the behavioral equation of combined biaxial bending and axial compression. And as you can see, if some of you don't notice, there is an error in this illustration, and that is because we're looking at compression, the arrow should be going that way. Maybe some of you have already pointed that out, but yes, we're aware of it. And what we have is short, when we're looking at combined axial and bending, we have the short column check, then we have the bending strong axis and weak axis. And in the 2012, there was a new equation to check this flatwise bending, because it was found that this flatwise, the lower denominator of this equation, could come up with some false results because it would go to negative. So to check that flatwise bending, we now have a new equation that was introduced in the 2012 NDS that's shown here. We also have some applicable factors related to bearing area factors, depending on if you've got, if you're checking your studs, for example, bearing on a sill plate, this factor would apply. You see some efficiencies when you have LB, the bearing length, narrower. You get up to a 1.75 increase in your bearing factor, and all the way up to 1.0. If you're over 6 inches or more, it's just 1.0. Also, for the actual behavioral equations, or long-term, when we're looking at deflection of actual members, if we're dealing with long-term loading or creep, you would see a new factor related to cross-laminated timber. And this is a time-dependent factor which deals with the time-dependent deformations of creep related to cross-laminated timber. And the factor is 2 because it's associated specifically to dry conditions. If you have something other than that, then you can't use this factor. And it's consistent with the 2.0 factor that's used for wood structural panels, similar to what is in dry service use. Also, you should look at the commentary related to the column stability factor, which now it's a column stability factor, which you see the equation there. And in that column stability factor, we have a new factor related to cross-laminated timber, and it was there for the glue-lam, but it's similar to glue-laminated beams. We now include cross-laminated timber into that. But it's recommended that when the NDS is developed with a commentary, you should make sure that you look at the commentary to make sure you're not using that factor incorrectly, to make sure you have the correct application of that C factor for C sub P. Okay, now another poll.
All right, here we go. E minimum is used for buckling calculations for bending members and compression members. Is that true or false? All right, I'm going to give you about 10 more seconds to get your vote in. Again, remember these are just polls. They're not tests, or they don't affect your CEUs at all. All right, I'm going to go ahead and close. All right, so 78% of you said true, 22% said false. And the real answer is Michelle.
Okay.
Uh-oh. I'm not seeing your screen again.
Yeah, I'm clicking on it, and hold on, let me see if this works. Seeing it now?
There we go.
Okay. Okay, and the question is, E minimum is used for buckling calculations for bending members and compression members, and the answer is true. And as mentioned previously, this was introduced in the 2012 NDS because of the dual format, and because the previous equation was based on an ASD design, we had to introduce this E minimum to accommodate for both designs. Okay, and now we're going to switch it over to Buddy, who will be taking over for Chapter 4.
Okay, thank you, Michelle. I think we're all set now. Let me make sure that you're seeing my screen. I believe you are. And we'll get started now in the product chapters of the NDS. And toward the end of this section, we'll get to the new product chapter on cross-laminated timber, which is what probably most of you are here for today. But Chapter 4 deals with sawn lumber, and in that chapter we cover visually graded lumber, machine stress rated and machine evaluated lumber, heavy timbers, which are 5x5 and larger materials, and timber decking, which are 2x materials, not the 5/4 inch decking that has a span rated capacity, but this is the 2x material that's used in flatwise orientation as decking. What you begin to see in the materials chapters are tables similar to this one, which shows the applicability of adjustment factors. And so Michelle's talked to you about the adjustment factors in Chapter 2 and the design values in Chapter 2, along with the design equations in Chapter 3. This table provides a nice summary, if you will, bringing together all those design values, design adjustments, and application of several of the equations like column stability, C sub P, and the beam stability factor, C sub L. So, for example, for a bending design value F sub B that you would get out of the NDS supplement for lumber, you have a base design value of, say, 1,000 psi. That would then be adjusted by the load duration factor depending on the loading condition, a wet service factor if you're used in an exterior application, as Michelle mentioned, possibly a temperature factor, if it's an unsupported beam, a beam stability factor. The size factor would be applied for 2x4 up to 2x10 sizes. The baseline values are based on 2x12 sizes. So those are some of the adjustments that you'll see that are common to a lot of different materials in the standard. I mentioned the size adjustment factor, and you can see here the cursor for a 2x12, the baseline of 1, and then adjusting up based on the size model that's been developed through the ASTM standard. Note that that also applies to tension and compression values as well, not just bending values. If you're out on the West Coast or Northeast, maybe into Canada, you might be familiar with incising lumber to have the chemicals that are used to treat lumber penetrate to the depths that's required by the standards that are developed by the American Wood Protection Association, AWPA. And so when those incisions are cut into the edges of timbers or lumber, they use these small razor incisors to do that. It damages wood fibers in the surface of the lumber. And so when we damage those wood fibers, these adjustments, called the incising factor, are necessary to make sure that you account for that reduced section, if you will, in the wood member. And that reduces the strength and stiffness properties except for compression perp, which is a bearing property, so that makes sense that that would be a factor of 1. The repetitive member factor that we mentioned, the C sub R, is prescriptively set at 15% increase on bending design values for 2 to 4 inch lumber. If you're less than 24 inches on center, and that also applies to members that are in contact, so if you have a built-up member, it would apply as well. 3 or more of those with some sort of load distributing element. Load distributing elements can be gypsum, plywood, or nails if you have a built-up member where you could get that increase. And it's a pretty common factor, pretty well known, but I mention it here because we're going to contrast it a little bit later on when we look at structural composite lumber. We get to Chapter 5, that's for structural glued laminated timber. Again, you see the table for glue lam, comparable to what we showed for structural lumber, and the adjustment factors that apply for those various properties of structural glued laminated timber. There's a footnote here that talks about the beam stability factor and the volume factor. We'll cover that here. The volume factor is a similar approach to the size factor that's used for sawn lumber that we talked about a little bit earlier, but it also, in addition to accounting for the depth, accounts for the width and length of the glued laminated timber product as well. And so that's called the volume factor. The beam stability factor is calculated according to the equation that Michelle showed earlier in Chapter 3, and those are not cumulative. So you need to calculate both in your design process and then use the minimum of those two factors in the design process. Round timber poles and piles are covered in Chapter 6. Poles are primarily used in post-frame construction. The large end of the pole goes into the ground for pole design. Piles are typically driven into the ground for foundations, and in that case, since they're driven, the narrow end of the pile goes into the ground first. And in the last go-round, 2012 NDS, we moved the design values for poles and piles to the NDS supplement. And so if you're looking in Chapter 6 for those design values and they're not there, turn to the supplement. We'll talk a little bit about that closer to the end of the presentation today, but there's where you'll find the design values for poles and piles in the NDS supplement. Again, a table similar to what you've seen in the NDS for lumber and glulam, lays out the adjustment factors, and some of these you see are very specific to poles and piles. A critical section factor and a load sharing factor are unique to poles and piles. A condition treatment factor, C sub CT, and so be aware that those are unique to that product, and that's why they only show up in this particular product chapter, as opposed to load duration or temperature factors that are pretty much uniform across all wood products. When we get to Chapter 7 for prefabricated wood I-joists, I-joists are proprietary products, and the design values are tabulated as moment shear and stiffness. Those values are incorporated in evaluation reports, and so they contain proprietary design values and therefore are not tabulated in the NDS supplement. So there are questions about whether those would eventually be incorporated into the NDS or NDS supplement in a more prescriptive way, and until the manufacturers decide to develop what are we'd call generic or commodity design values for those products, those remain proprietary products, and so you have to go to the evaluation report of the manufacturer to get those design properties. But once you have those design properties, you would look at a table like this, and there's some design provisions in the NDS that show the application of the adjustment factors, load duration, wet service, temperature factors to those products. But again, look carefully at the evaluation reports, because those may have overrides that are unique to those specific products. We get to Chapter 8, structural composite lumber. And Michelle showed this graphic earlier, but again, the design values are proprietary based on evaluation service reports from the manufacturers. And here, though, we see that for products like structural composite lumber, the coefficient of variation in those products is much tighter. In this case, we're taking wood fibers and sort of engineering out characteristics like knots and wane that would occur down here in lumber or machine evaluated lumber products, or even glulam that's made up of lumber. So the coefficient of variation for those products tends to be a little bit greater, much tighter with these other products, and so you can take advantage of that, and the manufacturers are taking advantage of that in the design process for those products. Here's something new to Chapter 8, the NDS, the 2015 NDS, and that's the introduction of two new products, not new to the industry, but new to the NDS. There are products out there called laminated strand lumber, or LSL, and oriented strand lumber, or OSL, that are described in the ASTM standard D5456. And so those have now been incorporated, and these are all part of the family called structural composite lumber, which also now include in the 2012 NDS and now in the 2015 also includes laminated veneer lumber and parallel strand lumber, PSL. So LVL, PSL, LSL, OSL, all products that are covered in Chapter 8 of the NDS now. I mentioned the volume factor earlier for glulam, and mentioned before that for glulam that volume factor is not cumulative with the lateral stability factor C sub L. And that's also true for structural composite lumber if the volume factor that's calculated is less than or equal to 1. But there are cases where you can calculate a volume factor greater than 1. And in that case for structural composite lumber, it is cumulative with that lateral stability factor C sub L. So there is a distinction here with structural composite lumber as opposed to glued laminated timber that you should be aware of as well in the design process. Another slight difference, and something that we typically point out and mention for the repetitive member factor for lumber, it's 1.15, and for structural composite lumber you can use that repetitive member factor, but it's only a 4% increase. And again, that kind of goes back to what we looked at earlier, the graph that showed the tighter coefficient of variation for these products. Since there is a tighter coefficient of variation, a lot of the strength properties are going to be much higher, and so we're not going to be taking as large a factor or an increase on the bending values because of that. So I'm going to ask Marcy if she would to come back, and we've got another poll question that you can get ready for here.
Absolutely. Here we go. New products included in the 2015 NDS Structural Composite Lumber chapter include the following: laminated strand lumber, LSL, oriented strand lumber, OSL, oriented strand board, OSB, all of the above, or A and B. Go ahead and vote. I'm going to give you about 10 more seconds. Here we go. And let's see, 76% say A and B, so LSL and OSL, and 21% say all of the above, and then just a couple people said A or B. So let's go back. There you go, buddy. Tell us what the real answer is.
Okay, and the real answer is A and B. So answer E is correct, and 76% of you got that right. Congratulations. Glad to see you're still paying attention an hour into the program. So moving on to Chapter 9. Wood structural panels. The design values, again, since we don't yet have generic design values for wood structural panels, you'll find those from different sources. We do publish some of those in the NDS commentary. We're hoping at some point to roll those into the NDS supplement, but I just want you to make note of the way the design values are shown for bending, tension, shear, compression, stiffness. The approach is just a little bit different from what you see of other products, and the reason I point that out is because when we get to cross-laminated timber in a little bit, you're going to see some similarities in how we approach design properties for cross-laminated timber. So again, you'll see a table 9.3.1 looks like this, and again the adjustment factors that apply to bending include load duration, wet service, temperature, and panel size factors. So you can see here that those factors or the application of those factors comparable to what we see for other products as well, but some are unique to wood structural panels. I want to point out the wet service factor on some of the strength properties, C sub m of 0.75 and stiffness of 0.85, so that's a little bit different than what you see for lumber and some of the other products. The temperature factor is based on an equation rather than a table that we have for other products, so be aware of those nuances for these very specific products. So now we're at Chapter 10 of the 2015 NDS, and if you've downloaded your free view-only copy or purchased a copy that you can print or make notes in, you notice that we have a new Chapter 10. So this is going to take a little getting used to. It's a challenge for me as well because I'm used to going to Chapter 10 and seeing connection design. So we'll all kind of learn this one together, but the new chapter on cross-laminated timber is Chapter 10. And since this is a new program and we're flipping along pretty quickly, I'll probably jump over into a PDF here in a second to take a look at that. But you see some of the provisions that we lay out here are again very similar to what you'll see for panel design. Notice the ANSI APA standard, the product standard for manufacturers to use in manufacturing of cross-laminated timbers, and that's referenced in both the NDS and the 2015 IBC as well. So you've got the code references for cross-laminated timber. You see the table here, 10.3.1, that shows application of the adjustment factors to cross-laminated timber, and again the way the bending, tension, shear, rolling shear, compression, stiffness properties are laid out, very comparable to what you see for structural panels. And so before I jump away from there, let me head over to the PDF that I had opened here, and let me pull that up, and we'll just we'll take a look here at the PDF and see if we can walk through this a little bit in a little bit more detail. Kind of waiting for the screen to catch up. I can see it's lagging a little bit, so let me give that a second. I mentioned the ANSI APA standard, so I'll highlight that. We've got a definition then in 10.1.2 for cross-laminated timber. It's going to consist of at least 3 layers of solid sawn lumber, and the adjacent layers are going to be cross-oriented and bonded with a structural adhesive. And so that's how it's defined in 10.1.2. Notice here in the dimensions that products can be or that the individual laminations can be as narrow as 5/8 of an inch up to 2 inches, but that the max is a 20-inch thickness. And then we mentioned the design values coming from the manufacturer. Let me see if I can adjust this a little bit so that I can see my dashboard, so I'm seeing a little bit better what you folks are seeing out in the audience. Notice that the moisture content is assumed to be 16%. again, comparable to some of the other engineered wood products that are used out there, and that if you're going to use it in a higher moisture service condition, that has to be specifically permitted by the CLT manufacturer. So again, as a proprietary product, the cross-laminated timber design values are going to have to come from a code evaluation report. Again, you see down here in 10.3.1, those design properties are shown very similar to what we see for structural panels with structural panels. The low duration factor applies except for stiffness, rolling shear, and compression perpendicular to grain. So again, comparable to other products and engineered wood products, we're not going to apply low duration factor to stiffness, rolling shear, or compression perp. So we've seen the adjustment factor table already. Let's jump down here a little bit. Again, that wet service factor, you need to get specific permission from the manufacturer to use these products in wet service applications. The temperature factors comparable to lumber up to 150 degrees, and again, those would be coming from likely from the manufacturer, but or no, I'm sorry. In this particular case, you would multiply by the temperature factor specified in section 2.3.3 of the NDS. Curved products is outside the scope of the NDS. So if you have any curved cross-laminated timber products, you'd have to work with your manufacturer to take care of that. The beam stability factor as it's applied to the bending design values. We're going to be, as Michelle mentioned, developing commentary here first quarter of 2015 for the NDS and the other standards that we've developed. And so as that commentary is developed, it will have more specifics about application of the beam stability factor and the column stability factor and its application to cross-laminated timber. So stay tuned and look for some more guidance to be coming out from the industry on application of these products. Again, it's brand new. As I understand it, there's 1 or 2 manufacturing plants in the U.S. now, and so we're a little behind the curve, but trying to catch up and help get information out there on using these products for design. Similar to other products, the bearing area factor can apply to compression perpendicular to grain. You could preservatively treat these products, again, depending on the manufacturer's recommendations. And in that case, similar provisions about the reference design values and not using a low duration factor greater than 1.6 for those products. Then application of the LRFD factors shown here as well in the remaining 3 sections. One last consideration at the end of the chapter is for designing for shear deformation, and you can reduce the effective bending stiffness of the product, EI, by use of this equation 10.4.1 and the adjustment factor K sub S, the shear deformation adjustment factor, is shown in this table 10.4.1 over here on the right. So again, some additional guidance for design to account for shear deformation if that's not already accounted for in the design values for that product. So that's a thumbnail view of Chapter 10 in the NDS. We didn't go into a lot of detail here in the slides because, again, as a new program, we weren't exactly sure about timing. So since we're a little ahead in the presentation here, thought we'd take some time to to work through some of those provisions. Now we get to Chapter 11, and again, for those of you like me who are kind of struggling to get used to the new format, what used to be Chapter 10 in the 2012 NDS is now Chapter 10 was now Chapter 11 in the 2015, and that deals with mechanical connections. This is sort of that catch-all chapter, has the same design table. Let me back up here. Now 11.3.1 that shows application of the adjustment factors for different types of connections. And so now Chapter 12 is going to be your dowel type connectors. Chapter 13 will be split rings and shear plates. And Chapter 14 will be timber rivets. So again, that's as much as anything going to be the toughest thing to get used to with the 2015 NDS. So no significant changes here other than a new chapter designation. So Marcy, I'm going to ask you to come back. We've got another poll question here, and let's see if folks are still with us.
All righty, here we go. So the NDS provides reference design values for A, nails, bolts, lag wood, screws, B, split rings and shear plates, C, timber rivets, D, all of the above, or E, A, and B. All right, go ahead and vote. About 10 more seconds. All right, I'm going to close the poll. Sharing the poll, and let's see, 76% say all of the above, 21% say A and B, and just a scattering here and there. All right. And the real answer is, buddy?
The real answer is D, all of the above. And so we do have design values for dowel type connections, split rings and shear plates, and timber rivets. And we'll talk about each of those three in the next few slides. So let's jump right in then to Chapter 12, which is dowel type fasteners. And again, new table references here. 12.3.1a lists the yield limit equations. I'm only showing the single shear yield limit equations here, but we do cover 4 modes of failure, 6 yield equations for single shear, 4 equations for double shear. We cover wood to wood, wood to steel, and wood to concrete connections. Let's talk a little bit about the different yield modes and how those apply. Mode 1 is a bearing dominated yielding of the wood fibers. So for single shear connections, you're going to have a large, maybe stiff dowel that is bearing and crushing the wood fibers in the main or the side member. Mode 2 is going to be very similar to that, where you've got fasteners that are rotating through, and so in these 2 yield modes, 1 and 2, we've got pretty much crushing of the wood fiber, so the wood fiber is controlling the design of these elements. We don't have any yielding of the fastener. So large bolts, 1-inch bolts, 3/4-inch lag screws, in a lot of cases, you're not going to get a lot of yielding of those larger diameter fasteners in those types of connections. Then we jump to mode 3. In mode 3, we begin to see yielding of the fasteners in addition to crushing of the wood fibers. So mode 3M, we get primarily crushing of the wood fibers in the main member. So probably got a thinner main member or lower specific gravity in this member. 3S designates where the side member is yielding, and so we've got a lower specific gravity in this side member or a thinner side member here to begin to see that plastic hinge form in a mode 3S. Then mode 4 is where we really see the fastener doing all the work, so to speak, and your shear walls, nailed type connections. You're going to see this type of yielding where the plastic hinge is forming on either side of the shear plane. And so what you begin to see with these yield mode equations and the way they're set up is that you can actually design different yield modes into a fastener. And so if you want a very ductile type fastener to be used in wind or seismic applications, you can work through those equations to get to a mode 4. And that then assures you that you've got the fastener yielding and doing all the work in that particular application. I know the equations can get a little unwieldy, but we do have a calculator on our website, a connections calculator. It actually calculates all of these yield modes for the different types of fasteners and spits out all the different yield modes, and so you can see what would actually control in the design process. So if you haven't seen that yet, I encourage you to take a look on our website for the connection calculator, and you can use that tool for your design applications as well. But I mentioned that the wood fibers crushing in a lot of cases will control the yield mode, and that's characterized by what we call a dowel bearing strength, F sub E. And so we have dowel bearing strengths tabulated for both lumber with different specific gravities, and you see specific gravity here in this table, and then for smaller diameter fasteners, less than 1/4 inch, so your nails and wood screws, they're not really dependent on whether you're parallel or perpendicular to grain with those fasteners. And so you've got one value here for smaller diameters. Once you get above 1/4 inch up to 1 inch and you're loaded parallel to grain, you still have one value because we didn't see a diameter effect parallel to grain for determining those dowel bearing strengths. But then once you get once you go perpendicular to grain, sorry, the heading got cut off here, but these are perpendicular to grain, then dowel bearing strengths, there is this diameter effect. And so the dowel bearing strength will have both a specific gravity and a diameter variable in the equation. You see the equations here that are used to calculate those values. We also have values tabulated for wood structural panels with diameters less than 1/4 inch. If you're using larger diameter fasteners for plywood or OSB, then you'll need to check on other sources to get those values. I believe APA has some information on their website that you can download to get those dowel bearing strengths for larger diameter fasteners as well. Then the other property that you'll need for those yield mode equations is the bending yield strength of the fastener itself. And here's from the ASTM standard that's used to test bending yield of nails. Those values are then tabulated in the NDS and footnotes and in Appendix I of the NDS. And so you'll need those bending yield properties as well. So that brings us to some of the new provisions in Chapter 12, which are related specifically to CLT, cross-laminated timber. So with for those of you familiar with the NDS, you know that normally for end grain there is a factor for withdrawal of lag screws, the factor of 0.75. So if you have a lag screw application in various wood products like lumber, and that lag screw is inserted in the end grain and it's going to be loaded in withdrawal, that adjustment factor for that withdrawal value is 0.75. So with the development of provisions for CLT, it's going to be really tough when you've got these cross laminations where you might have end grain in one lamination on one edge and then end grain on these outer laminations on this edge. And so to account for the fact that we're not exactly sure where that end grain can occur, you could have, remember, multiple laminations. It can go 3, 5, 7 laminations for these products. And to deal with the fact that, let's say you've got 1.5-inch laminations in these products, well, the edge distances for 1.5-inch lag screws actually start to run out once you get above about a 1/2-inch lag screw. And so, actually, I'm not even sure. Well, we'd have to think about that, but whether a 1/2-inch would work in a 1.5-inch cross section. So, to account for those variables, we just created a blanket provision that says if lag screws are loaded in withdrawal in the narrow edge of cross-laminated timber, we're going to apply that 0.75 factor regardless of the grain orientation. So it's conservative if you're in edge grain, like you see here, but it's going to be right on if you are inserting those fasteners into end grain. And so that's a provision that you want to be aware of as you get started into connection design for the cross-laminated timber products. The next one then has to do with withdrawal for wood screws, nails, and spikes. And comparable to the provisions that we currently have in the NDS for these fastener types, you're not permitted to load wood screws or nails and spikes in end grain of the laminations and cross-laminated timber. So we just very clearly spell it out so there's no confusion. Now, if you are in the edge grain, so if you're in edge grain like it is shown here, then it is appropriate to apply the factor that is used for wood screws, nails, and spikes in end grain. I can't remember what that is off the top of my head, but the provisions are in the NDS that allow you to do that. So no to end grain, yes to edge grain for withdrawal. So then we move to dowel bearing strengths and calculation of dowel bearing strengths. And so for fasteners that are loaded on, say, the face grain of cross-laminated timber, it's going to be pretty comparable to what you do now for lumber. If you're loaded parallel to grain, you're going to use the parallel to grain dowel bearing strength. If you're loaded on the face of these panels perpendicular to grain, then you're going to use the perpendicular to grain dowel bearing strength. And those are tabulated here. You'd use them just like you would any other fastener type. However, if your fasteners are installed in the narrow edge, so if you're now installing in the edge of cross-laminated timber, for dowels that are less than 1/4 inch, so your nails and wood screws, you're just going to use the dowel bearing strength FE as shown here for those products. So wood screws, nails, and spikes less than 1/4 inch diameter use this dowel bearing strength. But if you're installed in the narrow edge of cross-laminated timber and your perpendicular, or you've got diameters greater than or equal to 1/4 of an inch, then you're going to want to use the FE perp value that's shown here depending on the diameter of your fastener. And again, that's accounting for, it's going to be conservative if you end up in parallel to grain loading, but this then allows you to come up with capacity for those different types of fasteners. Now, if we're in face grain, so the dowel is, say, let's go back into the face grain of the cross-laminated timber. So we're not in the edge, and we're loaded parallel to grain. So note that we're saying you're loaded parallel to grain. We know that the fastener could penetrate through that outer lamination, say that 1.5 inch outer lamination, and then the next ply is going to be perpendicular to grain. So now we've got one ply loaded parallel to grain, the next ply loaded perpendicular to grain. And if you look at our technical report 12, you see that there's non-uniform loading of fasteners that are covered there. We've kind of got that same situation here where we're one layer parallel to grain, one layer perpendicular to grain. So we then are going to use this ratio of FE perp to FE parallel to adjust the length of those fasteners. And that's kind of complicated to talk about, so let's look at an example. I think it'll make it a little bit clearer for what we're trying to accomplish here. So let's say that we've got a bolted connection, and it's through a 3-ply CLT product. And so we've got a 1/2 inch bolt, and it's southern pine, so the specific gravity is 0.55. We need to determine an adjusted length of the main member. Let's say the side member is this steel side plate that's loading up this main member. So if we were to just add up the thicknesses, T1, T2, and T3, we'd come up with 4.5 inches. But again, we mentioned that middle lamination is now loaded up perpendicular to grain. So we're going to just take a dowel bearing strength for that particular fastener. So we're going to use the parallel to grain dowel bearing strength, and then the perpendicular to grain dowel bearing strength to come up with a ratio, 3650 to 5550. And multiply that times the thickness of that middle ply to come up with our 4-inch adjusted thickness. So that's the approach to get there, and that gives you then the design property you need for that particular application. The other thing that we've built into Chapter 12 are some end distance, edge distance, and spacing requirements. So if you look carefully at the diagrams and the tables that we provide, the tabulated values, you see that for parallel to grain applications and end to grain, we'll have some end and edge distance spacing requirements. For parallel to edge grain loading, we're going to have some end and edge distance and spacing requirements. Then we get perpendicular to end grain and perpendicular to edge grain, and we're going to have spell out the end and edge distance requirements for those. So designing for those products and paying attention to the detailing is going to be pretty important. But if you're doing fastener design now, you're used to accommodating end and edge distances for fastener design. So then let's get to the end grain factor, C sub EG. And so for end grain, and this is for our lateral design value, Z. So now we're not looking at withdrawal factors anymore. We're looking at our lateral factor, Z. For the typical fastener less than a 1/4 inch, that end grain factor is 0.67. So pretty much any end grain application, you're going to have an end grain factor of 0.67. But if the dowel type fasteners are greater than a 1/4 inch and are laterally loaded in the narrow edge of CLT, then we're also going to apply that end grain factor, again, regardless of grain orientation. So not knowing where the end and edge grain is going to fall, being able to account for those reduced end and edge distances for those larger diameter fasteners is we're going to apply this simplified or a conservative, I guess, approach of using an end grain factor of 0.67 on any CLT edge. Okay, so this is not new, but just a refresher for dowel diameters, and this changed in the 2012 version, so we kind of come back and refresh that each time because folks still ask questions about that. But for unthreaded full body diameter fasteners, we use diameter D for the design values, but D sub R for reduced body diameter fasteners and threaded fasteners. There's an exception. If you're not within a 1/4 of the full bearing length, and we'll show some figures here in a second that help explain that, then you can use that full diameter D. So the unthreaded diameter D shown here on the left hand, this left red dashed line. The root diameter in the threads shown here on the right red dashed line. Pretty comparable for the lag screws as well. So as long as your threads are not in proximity to the shear plane, so shear plane is here, as long as we've got those threads sufficiently away from the shear plane, either in the main member there or main member here, then you can use that full fastener diameter D. And so waiting for the slides to catch up there, I'm seeing that there's a little bit of lag, no pun intended. Then you can use that full diameter D. Then if you have fasteners that show up in the shear plane, you're going to use the root diameter D sub R in the design process. So this is just again a reminder. We do have a technical report 12, that's used for analysis of gaps between members, various bending moment configurations, fasteners through hollow members like hollow steel tubes, and fasteners with tapered tips. So that's a free download from the website that will allow you to take advantage of some of these applications and to potentially get your increases for the root if you end up with root diameters close to the shear plane. So I'm going to bring Marcy back and ask her to help us with a poll here again and see if you are still sticking with us.
There we go. All right, the yield limit equations for dowel type connectors account for the following. A, single and double shear. B, wood to wood connections. C, wood to steel connections. D, wood to concrete connections, or E, all of the above. All right. A little bit longer, probably about 10 more seconds. All right, I'm going to go ahead and close the poll. And then 83% say all of the above, 10% single and double shear, 6% wood to wood connections, and 1% wood to steel. Nobody says wood to concrete. All right. And Buddy, the real answer is?
The real answer is E, all of the above. So congratulations to 83% of you who caught that slide and have a good understanding of what's going on in the NDS. All right, so we can move along now. We got through those provisions. That's going to primarily cover the new CLT provisions. Split rings and shear plates, again, move to Chapter 13. That's going to be your biggest stumbling block. Timber rivets now in Chapter 14, so those end up in their new home as well. And just a point, because a lot of folks maybe overlook the fact that these timber rivets are very high capacity fasteners. You can get capacities of over 100 kips for timber rivets. So if you're looking for a real high capacity fastener, just so you know, those, if you haven't seen those tables yet, those are available. Also, we'll reiterate what Michelle mentioned earlier. Chapter 14 used to cover shear walls and diaphragms. We still reference the special design provisions for wind and seismic, but those are referenced in Chapter 1 now. And so Chapter 15 then is the same as it's always been for special loading conditions, and here we get our built-up column provisions, eccentrically loaded column provisions. We jump into Chapter 16 for fire design. There are a couple of new provisions here. Again, I'll mention that this chapter applies to columns, beams, tension members. Right now it's allowable stress design only, but the products covered include lumber, glulam, structural composite lumber, decking, and CLT. I misspoke earlier when I said we were done with CLT, because we've incorporated provisions in the fire chapter for CLT design as well. And so that's referenced now specifically in the IBC, the 2015 IBC, section 722.1 references Chapter 16 of the NDS. And so this approach, just in a nutshell, is based on the fact that as the outer layer of wood in a wood member burns away, it forms a char layer and protects the inner portion of that wood member. And so we account for that in the design process by assuming that that outer layer is sacrificial, and so we're going to design a reduced cross-section based on a char rate of 1.5 inches per hour, which is what's assumed for wood. And so we've done the tests and done the research and side-by-side tests, and you can see here in the comparisons of wood even versus steel that it holds up well in fire situations, and is actually a good product if used and designed properly. But there is testing that was done specifically on cross-laminated timber, and so with that testing where we got this 1 hour, or we got this, this wall assembly to pass over a 3-hour test. So we now have a CLT wall assembly that has a 3-hour fire endurance. We've got new provisions for calculating char rate and char depth in cross-laminated timber. So be aware of that. There's, again, another technical report 10 that gives the background on a lot of that testing, including design examples. The biggest change there is incorporation of floor assembly, lumber joist provisions. We're incorporating the CLT and some testing on structural composite lumber that was just finished up the end of last year, and so that'll be out later this year in an update to Technical Report 10 as well. So if you're interested in a little more information, there are a couple of papers that we've written. If you get Structure Magazine, the January issue had this paper And we now have permission to post that up on our website, so you can download that to get an overview. And again, Marcy, I'm going to ask you to come back and let's do one more poll.
Absolutely. All right. So Chapter 16 of the 2015 NDS on fire design of exposed wood members does not apply to which of the following products? Lumber, glulam, SCL, CLT, or wood structural panels? All right. Everybody's quick on this one. That's great. All right. About 10 more seconds. All right, and then I'm going to close. All right, 82% say E, wood structural panels, 7% CLT, 4% SCL, and lumber, and 3% glulam. All right, and Buddy, what is the real answer?
The correct answer is wood structural panels. Again, over 80% of you paying attention, getting the right answer here. So congratulations. All right. So we'll move then into the finale here. The appendix chapters are unchanged in the 2015 NDS. So to summarize, and you saw this slide earlier, CLT is really the big new thing for the 2015 NDS. We've got charging language, design values, which we say come from the manufacturer, some design equations, a new product chapter, connection design, and fire design to address cross-laminated timber. What's missing? We don't have shear wall values yet, so we don't have a response modification coefficient. It's not yet recognized in ASCE 7, so we're working on that in the interim. Some of your options are to do a performance-based design procedure per ASCE 7, demonstrate equivalence to an existing ASCE 7 system, or do a FEMA P695 or P795 analysis on those products. And we're actually working on all of those items at the moment, but if you are working with the manufacturer and building officials to try and come up with those values, that's how you'd want to approach it. We mentioned this in December with the 2012 NDS. There was an addendum that outlined new Southern Pine design values that came into effect in 2013. Those are now incorporated completely into the 2015 NDS, and so if you have any questions about information on those, there's some resources for you. So hopefully you've seen the free view-only download on the website. If you haven't, Brian can send you a link for that in the chat box, and you can go get your view-only copy. If you want a printable version that is a little more unlocked that you can do things with, you got to buy one. As soon as we finish up the commentary and some of the other resource documents, then we'll be printing copies of the wood design package, and those should be available sometime in the spring. Michelle and Marcy mentioned a webinar next month, February 19th, on seismic provisions for wood construction. So stay tuned, get signed up for that. Again, we've got some articles coming out in Structure Magazine. Oh, we're going to have to revise this one. I didn't make the deadline for the February issue of Structure Magazine, so that article got pushed to July. So we'll have to revise that, but we're working on it. So we'll keep you posted. And I'll stop there, ask Michelle to join me again, and see if we've got some other questions that came in during the seminar that we can try and address here. So Michelle?
Okay, can you hear me?
Yep.
Hello? Hello?
Yes, we're good.
You can hear me?
Yes, yes, I can hear you.
Sound like a cell phone commercial. Okay, Great job. Let's see. We do have a few questions, and one question had to do with what happens, and it has to do with connections, if the fastener is, we have end grain and side grain. What if the fastener is applied at the seam of the glue, where you have a joint, glue joint?
Yeah, and part of the reason that many of those adjustment factors that we talked about are sort of blanket adjustments. When you go into the edge of CLT, it accounts for hitting that adhesive plane.
And that takes account of the different directions of the wood, but that's correct. Yeah,
that's correct. So,
and I would also mention that similar to glue lam beams, where you don't know where the bolts go in the seam line.
Great point.
Yeah, that it accounts for those connections as well. I mean, you don't have a different direction in the wood, but you do have a seam there as well.
Yep, that's correct. That's a great point.
Yeah. Okay, the other question has to do with, let's see, could you review the repetitive member adjustment factor for structural composite lumber? Did it get reduced?
No, it's always been 1.04, and let me see if I can get there. So that value is unchanged, and if you're seeing my slides, it's again having a lag here. It's kind of hard to catch up, but
I'm seeing it.
Okay, so it's 1.04, and it's always been 1.04. So that has not changed in recent versions of the NDS.
Okay. And then there was another, maybe you could repeat it again. Someone was asking again if it's true that the publication is available for free.
Yes. Let me see if I can get there. Might as well.
Yeah, show them on the website how to get there. That would be good.
Okay, so you go to our homepage, which is awc.org. You're going to see some icons like this. Click on the Codes and Standards icon, and that's going to show you a cover of the NDS right there. So you click on that. This is going to get you to where you see all the different versions. So you go to the 2015 version, and that'll take you to this web page. And as soon as you click on the cover right here, that should launch your PDF version that you can download. It says here web view only in the title, so there's an end user license agreement that you're agreeing to when you download this. And again, it's not printable and has very limited commenting options, so it's just something that allows you to view the provisions, but that's about it.
Okay, another question. We had quite a few questions about when is the 2015 NDS going to be adopted?
And that takes me to the ICC website, because I was looking at this question a little bit earlier. So if you're seeing my screen now, if you go to iccsafe.org, they have a state adoptions PDF file. And this one was just updated in this January 2015. At this point, I don't see any states that are looking at the 2015 IBC. So the answer to the question is that as states begin adopting the 2015 IBC, the 2015 NDS will get picked up by reference in the 2015 IBC. Now, building officials all have the ability to approve newer standards, and most of them are likely to approve an ANSI standard, an ANSI consensus standard, even if it's, if they're not yet adopted in the code that they're enforcing in their jurisdiction. So, for example, if they're enforcing a 2012 IBC, they are very likely, if you work with them, to accept under alternate methods and materials, the 2015 NDS. So talk to your local building official, and I think you can probably work that out. And if you have difficulties or questions about that, we've got some folks that work in the field with building officials all the time that can help with that, and we'd be glad to. In fact, let me get you to our map that shows you those folks, and if you can see on the website here, that map, if you are in one of these different areas, these are the folks that can help you with some of those building official questions.
Right, and even some states, for example, Oregon, are adopting this as an alternate method. They've just recently heard this at a hearing, and I believe it passed to be used as a structural wood member.
Oh, okay, great.
Yeah. Okay, do we want to round it out? I think Marcy has or do you want one more question if I can?
No, let's go ahead. We've still got a couple more minutes, so if you have a couple more questions,
okay,
that'd be good to try and take those if we can. Let me pull up my question box here too and see what we've got.
Okay. Let's see, we have, what is the advantage of ASD versus LRFD or vice versa is one of the questions.
Okay, so I'm going to try and jump back, Michelle, to one of the slides that you talked about earlier on in the presentation, and the real advantage comes with multiple transient live loads. And so if you have applications, and this is true whether it's ASD or I'm sorry, this is true independent of your material type, but if you have multiple transient live loads, let's say you've got a multi-story building where you've got multiple roof and floor loads coming down through the walls, the load factoring that occurs in a lot of cases will help reduce those loads to the extent that LRFD is advantageous regardless of the material that you're using. So the first thing I would do is look at the load combinations of LRFD versus ASD to see where you get the advantage. You're probably going to have to do that anyway for your deflection calcs. You're going to need your ASD loads, and if you do your factored loads for LRFD, then you can compare to see which are going to give you an advantage in the design process. I think, Michelle, you and I had talked about updating a paper that we have on our website at some point that shows some of those differences. We've done that for the, I think, 05 ASCE 7, so we're going to take a look at that for the 2010 version as well.
Right. Okay, we're now up at the hour I have. Do you have that too on the East Coast?
Yes, we're top of the hour now.